we're moving on now to how to balance equations. So this is an equation, Sb2S3 plus HCl. So let's see, I see two Sb's on the left, so let's put a coefficient 2 on the right. That gives me 6 Cl's. Let's put a 6 in front of HCl, and then the 6H works out with the 3H2S. Okay, so this is a double replacement reaction, right? The Sb and the H flip-flop and take the other anion. So D from the same problem says Fe2O3 plus C yields Fe plus CO. So I see two Fe's, I put the 2 coefficient on the right, and then I just kind of work my way through on this one. This is a what type of reaction? This is a single replacement reaction. Okay, the carbon comes in, kicks out the iron, and singly replaces the Fe to take oxygen for itself. This is some new material here, okay? This is kind of like a new lecture material at the end of this video. Energy in chemical reactions. So, when a chemical reaction occurs, it's either going to release energy or it's going to require energy. So when a chemical reaction occurs, energy in the form of heat is either released is exothermic, or it's absorbed. Absorbed means required. Okay, released means like produced or gives off. So exothermic reactions, they release heat. If they release heat, a exothermic reaction in the test tube is going to feel hot. The test tube gets hot. Here's an example. You got 2 aluminum plus Fe2O3 yields 2 Fe plus Al2O3 and plus 850 kilojoules. That's because that's the energy released, right? Kilojoules is energy. Now, the way I usually write it is I just write the balanced equation the second way here. 2Al plus Fe2O3 yields 2Fe plus Al2O3, and then because energy is released, the change in energy is minus 850. And I'm putting that energy into a reaction energy diagram right here, where Ea is my activation energy. That is the energy that I have to overcome in order for 2 colliding reactants to move towards products. Okay, so activation energy, I will define it right here for you. It is the energy needed to break the bonds of reactants and then continue downhill towards products. Now here you notice that the products are lower energy and the delta E is a negative 850. This is what an exothermic reaction energy diagram looks like. Okay. Well, if the first one is exothermic reactions and heat's released, the second one is endothermic reactions, where heat is absorbed or heat is required or heat is needed. It's absorbed, and if you were to run a reaction like this in the test tube, it would feel cold to the touch because heat is leaving the surroundings and going into the reaction system. So I've written the 26 kilojoules as a reactant there because that's needed, it's absorbed. All right, now the way I like to do it and the way that most textbooks do it is they like to write the delta E after the equation. So here I have NH4NO3 solid. The presence of water becomes NH4NO3 aqueous. Okay, so just the act of dissolving NH4NO3, this is kind of like in those cold packs that you break. The delta E here is plus 26 kilojoules because the energy is required or absorbed. Now, the reaction energy diagram for this one is different. You'll notice that the reactants starts at one level and the products are higher up. That still doesn't mean we still have to overcome that activation energy barrier, right? We have to collide our reactants with enough energy to get up and over that Ea and downhill. All right. So the reaction energy diagram that I've drawn here is for an endothermic reaction, and the products are higher than the reactants, and the delta E is plus 26 kilojoules. Now, just a note, in both of those reaction diagrams I've just drawn, and in both of these sample balanced equations I drew, it says here, note, in both exothermic and endothermic reactions, the activation energy barrier, Ea, that hump, must be overcome in order for the reaction to move forward towards products. I don't know if you've ever been to the video arcade and you played skee ball, but when you roll the skee ball, it's got to go up and over that hump before it can move on and go in, okay? So three conditions have to be met in order for you to overcome this activation energy barrier, this big EA hump that you see on both of the reaction energy diagrams. First, the reactants have to collide, and then second, the reactants have to collide with enough force, right? So that when they have enough force, they break the reactant bonds and overcome this activation energy, and then they can form product bonds. And then the third one is that reactants must be aligned or oriented properly. So if this is what's needed for two reactants to collide, you wouldn't want them to collide like this. You'd want them to be aligned properly so that they can move to products. All right.